Question 6 is a continuation of question 5, which is the probability question about mismatched stocks. So this is a hypothesis testing question. So Professor Adhikari tells Professor Fithian that she also gets mismatched stocks a lot, and she says that there's a 25% chance that whenever she gives a lecture, the stocks are mismatched. So you think that that's an over-exaggeration, and that the true probability of her getting mismatched stocks is less than 25%. And you get an observed value by watching the last 100 lectures to see how many mismatched stocks there are. Okay, so question A is, which options are possible null hypotheses? And there can be multiple correct answers. So the first one is that in 100 lectures, Professor Adhikari is expected to wear mismatched socks about X times, and any deviation from that is blank. So this is one of the correct answers. The official solutions actually don't regard this as a correct answer, but points were given for it. And so the answer is she's expected to wear mismatched socks about 25 times because she said a 25% chance times 100 lectures is 25. And any deviation from that is due to chance, and not the fact that like the true percentage might not be 25%. Okay. The second possible null hypothesis is that Professor Adhikari's socks are just as likely to be mismatched or matched, and the rest of the option doesn't matter, because this is instantly wrong as soon as it says equally likely to be mismatched or matched, because that implies there's a 50% chance of being mismatched, but she says it's 25%, so that doesn't work. Okay. The third option is that Professor Adhikari is just as likely to sleep on the day of a lecture, and again, you can just stop reading right there. That's also incorrect, because it's testing a completely different thing. It's talking about if she goes to sleep or not, but that's not what we're testing. Okay. The next option is that if we label each of Professor Adhikari's lectures as mismatched or matched, then 100 lectures will be like a random sample drawn blank replacement from a distribution that assigns a blank percent chance to a lecture being mismatched and a blank percent chance to being matched. So this works. One of the key parts of a null hypothesis is the idea of it being like a random sample, because it gives a model to sample under, and it is drawn with replacement to prevent any statistical bias from being introduced, and it's assigning a 25% chance of being mismatched and a 75% chance to be matched. Okay, so this is a correct answer. Okay, next is Professor Adhikari wears mismatched socks as often as Professor Fithian wears mismatched socks. And again, you can stop there because there's no comparison being drawn between the two professors in our claim. So this is not right. Then the last one, in 100 past lectures, Professor Adhikari wore mismatched socks exactly blank times. So this is also incorrect, because even though we can plug in 25 there and make it look right, a null hypothesis is never saying exactly X number of times. It's giving a model that we can simulate under, and obviously in a simulation there can be a lot of variance. So that's not correct. So these two are the correct answers. Okay, part B. So one of these choices below is the correct alternative, so we want to figure out which one it is. Okay, so Professor Adhikari is less likely than Professor Fithian. This is incorrect because it establishes a comparison between the two professors, which I already said is not made in the question. And that's the same reason why the second option is wrong. So now, the probability she wears mismatched socks is less than, more than, or different than a certain number. So let's scroll back up and look at what we think. So we think that she is just exaggerating to make Professor Fithian feel better, meaning that we think we are mismatched less frequently than she claims. So the alternative hypothesis is our claim, so the answer is this one. The probability the socks are mismatched is less than 25%. Okay. Now, we watch the 100 videos and we count how many times the socks are mismatched. Which test statistic should we use? The total number of lectures with mismatched socks, or the absolute difference between the number of lectures with mismatched socks and 25? Okay, so the answer is the first one, just the discrete number of mismatched lectures. The reason why is because in our alternative hypothesis, we are specifying a direction of difference, meaning that, let's say it's off by 5, so 30% versus 20%. A value of 20% would support our null hypothesis, whereas a value of 30 would reject it. However, under this test statistic right here, they would return the same test statistic, which is 5. Whereas in the number of lectures with mismatched socks, it accounts for the fact that we only want to look for numbers that are less than 25%. Okay, part D is to fill in this code to simulate the value 10,000 times. Okay, so sim proportion under null is a function that, or this sim statistic function is a function where we can calculate one value of the test statistic. So to find the proportions under the null hypothesis, the best function to use is sample proportions. And so sample proportions takes in two arguments. It takes in the number of times you want to simulate, and it's going to be 100, because there were 100 lectures. And the second argument should be an array that adds up to 1 of the simulated, or of your probabilities. So we want 0.25, comma 0.75. 0.25 is the probability of a mismatch. 0.75 is the probability of it being properly matched. And since we want the number that are mismatched, we want to take item 0. Because sample proportions returns an array that also adds up to 1 of 100 random draws using these probabilities in the array. Okay, so now we want to return sim proportion under null. And since our test statistic is the number of mismatched lectures, we need to multiply this by 100. Because sim proportion under null gives us a number between 0 and 1, and we need to multiply that by 100 to figure out the expected number of times in 100 lectures. Now we have statistics equals make array, and this is our general syntax for a for loop. So we can do for I in np.arrange 10,000. New statistic equals sim statistic, because we just want to get one value right now. And then we want to take that one value and add it to our array. So the way we do that is by using np.append. So statistics equals np.append statistics new statistic. And so when we do this for loop, it'll put 10,000 simulated values into this array statistics. Okay, part E. These two histograms involve the number mismatched in the left one and the distance from 25 in the right one. Okay, so in these 100 videos, Professor Adhikari's socks are mismatched 16 times. So based on the figure above, which is the closest to the p-value? So let's draw a line at 16. 16 is right here-ish. Yeah, something like this, right? And note that we can just throw out this histogram from the start, because our test statistic is not the distance from 25, it's the number mismatched. So we're just going to completely disregard this histogram right here. So our p-value is the percentage of values that are more extreme than our observed statistic. So more extreme in this case is going to the left, because fewer mismatched socks indicates further away from the null hypothesis of 25%. So we need to find the area of to the left of basically this bar. So we can use the histogram area formula, which is just the area is the width times the height. So these bars on the x-axis have a width of, let's see, it has a width of 1, as it says in the question. So the width is 1, and then the height is in terms of percentages. So, oops, sorry about that. So we can take the height, which is 1%, the width is 1, so in this square right here, the area is 1%, and then for the smaller ones to the left of it, right here, we can basically say they add up to about 1%. They add up to about the height of the biggest bar, which means our final answer is closest to 2%. I know this isn't a super rigorous calculation where we measure the height of the bars, but given that we know it's going to be bigger than 1%, then we can look at the bigger options, and it's clearly not as big as 4 or 10%, so it's just this one in the sweet spot in the middle. Okay, and then part F is that if we use a 3% cutoff for the p-value, does the test favor our belief? So, since our p-value of 2% is less than 3%, we are going to reject the null hypothesis, and so basically we're going to say that we are right and the professor is incorrect.